Okay, in lesson 79, we're going to be talking about De Moivre's theorem. So that is a French spelling there, so I probably don't even say it right, but De Moivre. So De Moivre's theorem. Now it's related to, let's say, when we had something like, A times the cosine of theta, CIS theta, and we multiplied that times B cis theta. This would be, well, we would multiply these two, so we get the A times B, and then we get cis, and we'd add these two, so we'd get theta plus theta. Okay, so we've already been doing that, and De Moivre's theorem is kind of related to this. So in particular, we're looking at, let's say that we have some number z, and it is our CIS theta. Okay, then we want to find what z squared is. Well, z squared would be r cis theta times r cis theta. Okay, and so using this property that we know when we multiply the polar forms, we get r squared, and then CIS, and it's going to be theta plus theta, so that would be 2 theta. Okay, let's look at z cubed. Well, z cubed is like z squared times z. We already know that z squared is r squared CIS 2 theta times z, which is r CIS theta. So to multiply these, we multiply the coefficients in front, the radii, so we get r cubed, and then CIS, and then we add the two angles. So 2 theta plus theta is 3 theta. Let's do one more. Let's do z to the 4th. Well, maybe we could write that as z squared times z squared, or we could do z cubed times z squared, whichever one you wanted to do. Okay, but if we substituted for those, well, we get r to the 4th CIS, and this time we add the angles 4 theta. So hopefully you're noticing a pattern. So in general, if we do z to the nth power, you can see what we're going to get. We're going to get r to the 4th power, or r to the nth power here, and then CIS, and 4, 3, 2, you see the pattern here. We're going to have n times that we've added the angle theta together. And this is De Moivre's theorem, that when you have z and you raise it to the nth power, it will be the radius to the nth power times cosine plus I sine times the angle, n of those angles. Okay, so that can come in handy in a few different ways. First, let's just do one of their examples. We want to find 2 CIS of 30 degrees to the 5th power. So rather than having to write them all out and multiply them, we know that using De Moivre's theorem, that's just going to be the 2 raised to the 5th power times CIS of this power 5 times the angle of 30 degrees. 2 to the 5th is 32, CIS of 150 degrees. So that would be the short and sweet. We already know that that's the way to do it with De Moivre's theorem, so we don't have to write them all out and figure that out over and over and over again that it's true. We can just go straight there. Okay. So one of the ways in which this comes in handy is consider this problem. We want to use de Moivre's theorem to find 1 plus I, that complex number, raised to the 13th power. Now, up to this point, the only way that we would know how to do that is to write down 13 copies of 1 plus I times 1 plus I times 1 plus I, and then use, okay, 1 times 1 is 1, 1 times I is I, and another 1 times I, and then we have an I squared, and we'd have to do this 13 times. Can you imagine how painful that would be? Very painful. Okay, but we know that if we can write our complex number in its polar form, and it looks now like this, and raise it to the 13th power, well, whatever in our polar form, we just take the radius to the 13th power times CIS of 13 copies of the angle, and we're good to go. So the first thing we want to do is just convert this to polar form, and then it should be a very, very simple problem for us. Okay, so imagine what the polar form of this would be. So we have 1 in this direction, and then 1 in this direction. So that would be kind of what we're looking at. So the radius in this particular instance, imagine we have, this is 1, so that's got to be square root of 2. So this is square root of 2 CIS, and what is this angle? Okay, well, if we have a line here with a slope of 1, rise 1, run 1, it's the angle that bisects this angle right here, right? So this is 45 degrees, or we just know it's 45 because it's a 1 square root of 2. But that's definitely a 45-degree angle there. So now that we've written that in its polar form, and we want to raise that to the 13th power, well, that's not so hard to do. We just do the square root of 2 raised to the 13th power, CIS of 13 times 45 degrees. Okay, so let's see, we have the square root of 2 raised to the 13th power. Well, so if we had it squared, it would be 2. So we'd have, 6 of, well, let's just go ahead and, so let's write this like, this would be like square root of 2 times the square root of 2 squared. Okay, and that's one of them. And then if we want the other 12 like this, if you want to think of it that way, that will help us figure out what that number is easily, I think. And then 13 times 45, I'm going to break out the calculator so I don't make a mistake. $585. Okay, so the square root of 2 squared, that's 2. And then 2 to the 6th power is 32, 64. So we would have 64 square root of 2. Okay, and then for this one, we would probably want to go ahead and get this back into, a 0 to 360 range. So let's subtract 360 from there. So we'll have a CIS of 225. So that is the way that we would write that one. Okay. So you can see how this came in handy so that we wouldn't have to write out and figure out what that complex number to the 13th power is. Okay, so that is the short of de Moivre's theorem. We can kind of see how useful it is. And we're also going to see that it's helpful in finding not just powers, like the 13th power, but roots, like the 3rd root or the 4th root or the 5th root. Okay, so before we look at how to use de Moivre's theorem to help us with finding roots, let's just think about roots. And think about, like, in problems where we have, 4, we say something like x squared equals 4, solve for x. Okay, And we always want to make sure that we do something like when we take the square roots of both sides and we want to find all the roots, that we say x is plus or minus 2. So there are actually 2 roots of 4. Positive 2 squared is 4, negative 2 squared is 4. And we don't want to forget either of those roots. Okay. And let's say we had something like x cubed equals 8. Well, we would take the cube root of both sides, and then we would usually, we're just going to say, well, there aren't any negative, we can't have a negative times a negative times a negative being a positive, right? So that's there's only one, you feel like, cube root, and that's 2. But actually, if you think about imaginary numbers, you can have a sort of a square root. So you could have like a negative number and then times a complex number times a complex number, and that would give you a negative number. So we normally think of this as only having 1 root, but there really are 3 roots. It's just that one of them is real, and there's 2 more complex roots. This is the only real root. But there are 2 more complex roots. And that's what we're going to look at today. How do you find those 2 other complex roots so that you're finding all 3 of the roots? And in general, whatever the power is, if you have, x squared, there's going to be 2 roots. And they're both real, a positive root and a negative root. If you have x cubed, there's going to be 3 roots. And in this case, we probably have like a 1 real one, 2 complex ones. If you have x to the 4th, you're going to have 4 roots. Sometimes you'll have two positive ones, 2 negative ones, something like that. Or you might get 2 positive ones, or 2 real ones, and 2 complex ones. In general, when you have x to the n, you're going to have n roots. They're not all going to be real, probably, but you will have n roots. Okay, so now the question is, how do we find those roots? So first of all, we're going to kind of work backwards on this. So we have 3 third roots of 8 CIS 36, and they are these ones. And let's just convince ourselves that those are all roots of 8 CIS 36, and then let's figure out how we got those. Kind of working the problem backwards almost. Okay, so on this one, okay, here, so if that is a third root, then when we raise this 2 cis 12 to the 3rd power, or better, get this. Okay, well, when we do that, we're going to get 2 to the 3rd power using de Moivre's theorem. And then CIS of, 3 times 12, which we have 2 to the 3rd of CIS 36. Oops, I should have written that as an 8. Sorry. So 2 to the 3rd is 8, so that's exactly what we were hoping for. 8 cis 36. Okay, how about this one? Okay, well, if we raise 2 cis 132 to the 3rd power, well, again, we're going to have 2 cubed, and then CIS of 3 times 132. So that, again, is 8. CIS and 132, we're going to get 396. Okay, and now that's, let's take that back to a coterminal angle that is in the 0 to 360 range. So that's the same as 8 CS, and if we subtract 360 from there, we'll get 36. Oh, great, that's just what we wanted. Okay, and then this one, 2 cis 252. Again, we have the 2 cubed. And CIS of 3 times 252. Okay, that's 6, 15, 7. Okay, so we have 8, 756. Again, let's subtract off 360 from there, and we get 8, actually, let's subtract off 720, right, instead. Okay, so when we subtract off 720, oh, yay, we get 36. Just so notice that each one of these gives us, when cubed, gives us the 8CS36. Okay, so now that we see that there are actually 3 roots, where did we get them? Well, we kind of start here. Think about when we used de Moivre's theorem. Okay, if we had 8cis36 and we wanted to work this backwards to get to here, well, we know that, this came from cubing whatever the original number was. So we would take the cube root to go back this direction. So we would take 8 to the 1/3 power. So if we want the third root, we take the third root of whatever, radius value we have on our polar representation, our polar form. Okay, and then how do we get back to this angle? Well, this 36 was 3 times 12, so to get backwards from here to there, we want to take that 36 and divide it by, I guess I should be going sort of back here. We're going to do 36, and we want to divide it by whatever that power was, 3. Okay, so this cubed value, if we take the cube root of it, we get back to the original value. How do we take the cube root of it? Well, we take the cube root of the radius value, and we divide the angle by 3 in this case, and we'll get back to the angle that we came from. Now once we get back there, okay, well, how did we get this one and this one? Well, hopefully you can see that these, we just had to subtract 360 from this one, we had to subtract 720. These are just shifted angles that are going around. So what value did we add? Well, whatever, we take our 360 and divide that by whatever power we raise to. Divide that by 3, that would give us 120. And that 120 is the difference. So if you added 120 to this one, you'd get the 132. If you added 120 to this one, you'd get the 252. Okay, so that is the value that we're adding. So you start with this one, and then we just have sort of these coterminal angles, and we get them by taking the period of cosine and sine, dividing it by whatever root we're going for, and that will tell us how much to shift the angle at each spot. Okay, so let's do an example of these. So we want to find the fourth roots of 16 CIS 60. Okay, so we're going to start and say, okay, well, if we want to find the fourth root, where did that come from? Well, some number had to be raised to the 4th power to get this. Okay, what number would have had to be raised to the 4th power? Well, it would have had to be the 16th, or the 4th root of 16. So we're going to find the 4th root of 16. Okay, and then what angle would we have? What angle would we have used? Well, by de Moivre's theorem, that would have been a 4 theta. So if we want to figure out what that theta was, we need to take the 60 and divide it by 4. Okay. Now in this particular instance, this means the positive 4th root of 16. This doesn't mean, oh, I have to take all 4 roots of 16 to figure out. No, it just means the positive 4th root of 16. Okay, so that would have been 2. And then this is CIS, and 60 divided by 4 is 15. So that is our starting point. Okay, and now we need to figure out what to add to get the other angles. Alright, so if we started out, if we have a period of 360, if we divide that into 4 equal pieces, that gives us 90. So the 90 is what we're going to want to add here. Okay, so we're going to add 90 to this. So our next root is 2 cis, okay, 105. And then we'll add 90 to that, and we'll get 2 cis 195. And then we add 90 to that, and we get 2 cis 285. And probably, you know, it's a good idea to check all of them and make sure they're correct, but let's just pick one of them and let's not check all of them in interest of time, but let's maybe do this one. Okay, so if we were to raise this to the 4th power, would we get the 16 CIS 60? Alright, so if we raise this to the 4th power, we would have 2 to the 4th, and then CIS of 4 times 195. Okay, 2 to the 4th is definitely 16, and then 4 times 195 is 780. Okay, and if we subtract the 720 off there, sure enough, we get 60. So raising that one to the 4th power gives us exactly what we wanted. You can try that on the other ones as well, but it should be correct. Okay. Alright, our next problem. We need to find 5 fifth roots of the imaginary complex number I. Okay, so to find the 5 fifth roots, first of all we need to put this in polar form. We have to have these in polar form if we want to get the benefits of de Moivre's theorem. So think about what this would look like. Okay, I, so there's no real component. There's just an imaginary component right there. Okay, so the magnitude of that is 1. And then the angle right there is 90 degrees. Okay, so we want to find the 5 fifth roots. Alright, so we're going to have the 5th root of 1. And then the angle is going to be 90 divided by 5. Okay, well the 5th root of 1 is 1. And 90 divided by 5 is 18. So that's our starting point. And then to find the other angles, we do 360 divided by 5. Goes in, so 72 degrees. That we need to add on there. So we'll also have 1 cis, and if we add 72, we get 90. And if we add 72, we get 162. And if we add 90 again, we get 252. And if we add 90 one more time, we get 342. 1, 2, 3, 4, 5. That should be all of them. Okay, so the one that's maybe fun to look at is this one right here. So think about what 1 cosine 90 plus I sine 90 would be. Okay, well cosine of 90, if you think about cosine of 90 is 0. So this is going to be 1 times 0 plus I times sine of 90. Think about sine of 90. The sine of 90 is 1. Okay, so this is 1 times 1I, or just I. Is I a 5th root of I? Well, yes, I to the 5th is like the I to the 4th times I, and we know I to the 4th is 1. Right? So that's So sure enough, I is one of the fifth roots. That's probably the only one of that we would have come up with. We probably wouldn't have come up with these other ones. That's kind of the one that we probably would have come up with. But there are 4 others, and here they are. And you could check them all if you wanted to, but they are indeed all fifth roots of I. Okay, we'll go ahead and do one more of these. Find the 3 third roots of -1. And probably in your mind you can think of one of them, I hope. But there are 2 more that you probably are not thinking of. I wouldn't expect you to come up with them. But again, we need to write this in polar form. So think about -1. Well, -1 would be over here, and that's the real part. There is no complex component, but okay, so if we're thinking about this, we've got a magnitude of 1 and an angle of 180 degrees. So that is 1 cis 180. Okay, we want to find the third roots. So we're going to have to do the third root of 1, CIS 180 divided by 3, or 1 cis 60. So that's our starting point. And then we'll do 360 divided by 3, which is 120, and we will add multiples of 120 to get the other angles. So we'll also have 1 cis 180 and 1 cis 300. Okay. Now, I imagine this is probably the one you were thinking about. You probably weren't thinking of it as 1 CIS 180, but let's, that would be 1 cosine 180 plus I sine 180. Okay, cosine 180. Well, that's down here, right? So this is a -1 plus I times sine 80. Well, here's the sine. Here's 180. That's 0. Okay. And so we have 1 times -1 plus nothing. 1 times negative, that's just -1. Okay, so -1 is probably the root you were thinking of. But what about the other 2? You probably weren't thinking about these ones. And let's see what those ones are. We'll write those in rectangular form as well. Okay, so this is the rectangular form for 1 cis 180. And then we also have, I'm not going to write the 1, this is cosine 60 plus I sine 60. And this one is going to be cosine 300 plus I sine 300. Okay, so 60 degrees, if we were to think about that. Okay, if this is 60, we've got a 1 and a 2 and a square root of 3. So cosine of 60 would be adjacent over hypotenuse, which would be 1/2. Plus I, and sine of 60 is square root of 3 over 2. So another of the roots of -1 is 1/2 plus square root of 3 over 2 times I. That complex number. Okay, and then this one, thinking about 300. So 300 is just shy, it's 60 degrees shy of our 360. Okay, and so this is 1. This would be 2. This would be negative square root of 3. Okay, so the cosine would be, again, 1/2. And then we have plus I, and the sine of 300 would be negative square root of 3 over 2. So the better way to write that would be 1/2 minus I times square root of 3 over 2. So that is the other. So those are the 3 roots of -1. Okay, so let me know if you have any questions.